Let's talk now about the problem of finding the area under a curve. Okay, let's start with a parabola. Okay, and let's say we want to find the area that is under the curve between x equals 0 and x equals 1. This area over here. And we want the precise value. Okay, you may already know how to find this using calculus, but if you haven't seen already that, how would you find this area? It is actually a difficult problem. There is no easy geometrical way, given a general curve, to find the area. So let's learn how to do it using calculus. The idea, as usual with calculus, is the idea of approximation. So what we are going to do, we are going to approximate the area we want to find by a series of rectangles that are under the curve Okay, and even though it's we are underestimating the area we want to find, it's still, it's something, right? So how do we do this estimate? So here, notice that I chose 4 points, 4 sample points that are 1/2, 1/4, and 3/4. Okay, 0.25, 0.5, and 0.75. So what we are going to do here is just use the formula for the area of a rectangle, which is base times height, right? That's the reason why I chose rectangles. And here, the length of the base is always 1/4, okay? Because that's how I built the rectangle. So it's 1/2 minus 1/4. This distance here is 1/4, 1/4, 1/4. So it's 1/4 then times the height. Okay, but the height is given by the value of the function at the sample points. So what I'm going to get for the estimate, this is just a side comment, is going to be 1/4 times f of 1/4, that is the area of the first rectangle, plus 1/4 times f of 1/2, the second rectangle, plus 1/4 of f of 3/4, and that's the third one. There is actually a fourth rectangle that I didn't write, but I'm going to write it now. It's a rectangle, the one that doesn't appear because it has height equal to 0, is 1/4 times f of 0. Okay, the value here, f of 0. So it's a rectangle without area, if you want. Okay, so this one doesn't really appear. So this is 0 plus 1/4 times 1/4 square plus 1/4 times 1/2 square plus 1/4 times 3/4 square. And then here we need to use the calculator, okay? But we get 7 divided by 32. Okay, you can use the calculator to to get the decimal expression for this. Okay, so here what we did was to underestimate. But you could argue, well, why underestimate? And that's fair enough. We could also overestimate. Let's draw the rectangles properly. And instead of taking those rectangles, we could take these ones. Okay, in this case, we will be taking this area. Okay, again, the same sample points. 1/4, 1/2, and 3/4. Okay, and in this case, as I was saying, we are overestimating. But again, this is also an approximation of the area we wanted to find in the first place. So in this case, we have 1/4 times f of 1/4. That's the first rectangle, plus 1/4 times f of 1/2, the second. There we go. Plus 1/4 times f of 3/4 plus, and here comes the new thing. You see, as before, we have 4 rectangles. 1/4 times f of 1. Okay, before there was a hidden rectangle because one of the rectangles had height equal to 0, but now we have 4, but all 4 are actual rectangles. Okay, so here we can compute. If we want, we can also factor out the 1/4. Let me do it that way. And we have 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. Those are the values of the function that are giving us the appropriate heights for these rectangles. Okay. And then again, we can compute this. We can compute it using the calculator. And we are going to get, I wrote it as a fraction, 15/32, but we can also write it as a decimal number. Okay. And something that we know for sure. Okay, this may not be a perfect estimate, but something that we have already learned is that the area we wanted is in between these two. In one case, we are underestimating, in the other, we are overestimating. Okay, so we have already an approximation. Notice that when we put this in the calculator, we get 0.22 basically, and we have 0.47. So actually it's an approximation, but it's a little poor, okay? We don't even get one correct decimal figure, okay? We know it's 0 point something, but that something is kind of unclear. But we could do something else. Okay, if you think about this, you can think about this as an image on the computer. Okay, here what we have is a problem of resolution. So this is 1/2. This is we divide as before, but we could say, well, let me take more rectangles and increase the resolution of the picture. Okay, when we take more rectangles, then it is clear that the approximation is going to be better. Okay, we are going to take these rectangles and we can do the same from above. Okay, in this case, we have these rectangles. There we go. That gives me the approximation. Okay, so actually if we compare the two pictures, it is clear it's like a pixelated picture. Still we can see the pixels there, but it's getting better. Okay, and if we keep going and going and going, you will agree with me that there will be some point that the image will still have pixels, but we will not be able to see them. Okay, so at that time it will still be an approximation of the area, but it will be very good. So that's the idea that we are going to apply. Okay, let me take note here. We are going to use more rectangles for a more accurate answer. Okay, this is what I was saying, is more resolution. Okay. So let's recap. Here, when we estimate the area under the curve, we get to choose two things. Okay, the first thing we get to choose is the number of rectangles. Okay, this is equivalent to choosing the width of the rectangles. Okay, the more we choose, the thinner they are, right? And the second thing that we get to choose is if we are going to take left endpoints, right endpoints. Okay, this is what we were saying. In this example with x squared, left endpoints was the equivalent of overestimating, and right endpoints was the equivalent, sorry, the other way around. Left was the equivalent of underestimating, right was the equivalent of overestimating. Okay, but that was because x squared is increasing. But we can also, there's a third option, which sometimes is used, which is using midpoints. Okay, sometimes instead of taking, let me copy this 3 times. So instead of taking the left or the right endpoints, sometimes we take the midpoint. Okay, which you see is somewhere in between. You lose a little bit on one side, but you gain it on the other side. So it's a bit more balanced somehow. Okay, it doesn't necessarily, depending on the situation, maybe a little better, but it may not be spectacularly better also. Okay, so we get the general setup with this. So what is the general setup? I'm going to write the type of problem we want to do and the general approach we have been describing. So we want to find the area under f of x on AB on an interval. Okay, so the first thing we get to choose is the number of rectangles n. Okay, so let's say we have a function like this. Okay, this is f of x, and here this is a, and we have here b. Okay, and we are going to take a as x. Well, this doesn't matter for now. We are going to divide this in a series of rectangles. We are going to have n rectangles. Okay, the width, we call it increment of x, is b minus a divided by n. Okay, so here this describes a series of sample points. The first one, x0, is a, and the goal is that the last one is xn. Okay, and then we have x1, x2, x3, and so on. Lots of points. Then the second step, we need to write down the sample points. X0 always is a. Okay, x1 is a plus the increment. Okay, x2 is x1 plus the increment again, or if we want, is a plus 2 increment of x. x3 is x2 plus the increment, or a plus 3 times the increment. And we can keep going. Xn minus 1 is xn minus 2 plus increment of x, which is a plus n minus 1 increment of x. And then the last one is xn minus 1 plus increment of x, which is a plus n increment of x. But then if I write what was the increment of x, which is b minus a divided by n, remember from here, this is a plus n times b minus a divided by n, which is b. Okay, and this was the goal. Remember, I was saying that xn should be b. That's why we are starting x0 is a. Okay, so this is, as I was saying, this is a general template. In an example, we just, instead of writing this in general, we do this on the spot, okay? But once we know this, then we can write the left and right sums. Okay, so the sum with left endpoints is going to be the increment of x times, that is the base of the rectangle, times the height, f of x0 plus delta x times f of x1, and so on, delta x, f of xn. Okay, but remember, no, not this xn, is xn minus 1. Okay, why is that? Because we need to stop on this one. Okay, if it's left endpoints, we need to stop where we have a left endpoint. So it will be looking like this. Okay. So n minus 1. Then remember, this x0 is a. So we can write this carefully, delta x, f of a plus fx1 all the way to fxn minus 1. Again, I'm just explaining the general method. Then on a particular example, we don't care so much about writing this in general. We just do it on the spot, okay? But instead, if we take right endpoints, so if we look here for right endpoints, we are going to take these rectangles. Okay, so now the first rectangle has the right endpoint. Okay, on x1. So this is f of x1 plus delta x, f of x2, and it goes all the way to the last one, but the last one is the one that has for right endpoint xn. Delta x, f of xn. So this is delta x, f of x1 plus f of x2 plus f of xn, which is b. So let's just write it. Okay, and this is the formula for the right sum. And then this is the reason why I was writing this in this way. Remember I said that the area that we want is somewhere in between these two. So the exact area, not an approximation, the exact one, is the limit of these two. Okay, and here the magic is that as we take a larger and larger number of rectangles, both these numbers are the same. Okay, so in the end, it doesn't matter if we were finding the right or the left endpoints. When the number of rectangles is huge, the difference is minimal, and in the limit there is no difference. Okay, they provide, and here is also very interesting. For example, in the initial example here, those limits are giving the exact area of the shaded region, the pink region, okay? Not an approximation, exactly the area.